My name is John Sumsion. I work for FamilySearch. If you've ever heard of that, we are a genealogical database and website where we publish a lot of records and run a global family tree for the whole world. I'm going to talk, this is the outline of the talk, I'm going to talk a little bit about FamilySearch Family Tree so that you understand the data model and why it is the way that it is. Then we'll get into some details. We are running right now on Oracle. We're using Oracle as a blob store, and we have persons and relationships, and we'll get into the detail and the scale and stuff in a minute. We have a very large single pedigree. In the family tree, there are between 900 million persons. They are lineage linked in that pedigree. How they are related to each other is recorded. We also host a very large collection of source document records, like indexed, scanned. In various countries, records are kept of when people were born, when they were married, that kind of thing. And we digitize that, index it with the help of a large volunteer group of people and publish it. And we run a genealogical library in Utah. The FamilySearch is the family history department of the Church of Jesus Christ of Latter-day Saints, otherwise known as Mormons. So if you haven't ever seen a Mormon before, here, I'm one. All right, if you want to know why the Mormons care about family history, you can visit this link, mormon.org/familyhistory. And I'll just let you do that based on your interest. The records, indexing, community, memories, all of that feeds into this family tree. Records die all the time. You would be very surprised about archives burned down. There's mass record destruction that happens all the time. There are floods. People die, and the records that they collected during their life are not of value to anyone anymore and just get thrown in the garbage. And so we're motivated to try to capture those records in a timely way and make them accessible. We capture those records. Microfilm was a technology that we used back a while, but we're now capturing digital. We store those records also. So 3.5 billion indexed records is where we were at when I checked the site. We index about 35 million records a month. We'll get to the Cassandra stuff, and this is very short here. Memories, we let people put in stories about their ancestors and about their family. We also run a Wikimedia site that gives research guidance. All of this kind of leads to the family tree project that I'm going to talk about. All of that data ends up being accessible and useful to people when they're putting their stuff in the family tree. So 500 million person records, it's an open edit system. So if you want to change information about a person, similar to the way you would edit a Wikipedia article, you would go and say the person was born in 1908, not 1907. You found a new record, you'd say why you think that way. The relationships between those persons, 500 million, there are couple relationships and parent-child relationships. Those relationships are also open edit. In the history of the family tree since 2012, there are almost 8.5 billion change entries. We track changes. And right now it's live. You make an edit, you see the result. There's no batch update process before you see the result. And we have some really interesting data-dependent performance issues, like persons who have 1,000 sets of parents, or a person who has 500 spouses, because there were 500 different copies of that person. Similar to the last talk, I was nodding my head the whole way through about fuzzy matching, because we do a lot of that. We then take that pedigree and in interesting ways, and in ways that are like really hard to do in one thread on an app server. We produce displays similar to this. This is a 9-generation pedigree. It takes about 30 seconds to compute this and render it. There are 500 persons on that one thing, and you can think, we're running it out of Oracle right now, so that's at least 500 primary key fetches and at least 500 global index scans to find related persons. This is an example of what the family tree looks like. The different persons are linked together by their lineage. This page right here happens thousands and thousands and thousands of times every day, but it's really expensive to compute. We also track, there's a screen called the Ancestor Page where it shows related persons and all of the changes that have happened, or the most recent changes that have happened on that person. That's hard to render. Right now, this change history page takes 2 or 3 seconds, which is horrible. So we're looking for a more performance solution. We're also looking to pay less database license cost and something that meets the reality of our system, that solves the performance problems for large families, for large change histories, and for large pedigrees. So I want to show you illustrate the index problem. In order to traverse from one person to another person in the current system, there's a relationship table that sits in between. To query that relationship table, we have to have a great big global index. That great big global index is 300 million rows big, and a range scan on that global index costs somewhere, we've tuned it, and it's somewhere around 5 milliseconds. But we do a primary key read on the person, we do a global index scan on the relationship, and we do another primary key read on the person. The change history, 8.5 billion rows in that global index, that costs a lot. So taking a big step back, we were looking for other alternatives when we saw Cassandra and said, hey, let's do it. So we did a full data scale proof of concept. We imported all 8.5 billion change entries in and looked at it. And we could not believe the result. It was just amazing. We'll get to the stats at the end. But we had to reinvent the data model, and we had to reinvent a consistency model. We were using optimistic concurrency, update, where ID is this and version is X. And that didn't work anymore with the distributed database. So let's talk about the reimplementation. We picked an event source data model. So the truth is in the journal, and the view is computed from the journal. And we keep that up to date incrementally. And we don't have to have any indexes at the moment. We're most of the way through reimplementation, so this is kind of a work in progress for us. But primary key indexes is the only thing that we do. And we were able to satisfy the consistency. So this is the core of what I'm trying to present, is the consistency in the data model. So for person 1 and person 2, they share the same relationships, 2 of the same. Let's say person 1 and person 2 are spouses. So relationship 2 would be a couple relationship. And then let's say that person 1 and person 2 are parents to the same child. So relationship 3 would be that parent-child relationship. We store the relationship in as many different person records as it is present, and it's stored the same way in all of the persons. So that is what let us get rid of the index range scans, the wide queries, and just go from one person to another person with primary key fetches. We had to denormalize the relationships in order to be able to do that. But that created an additional problem, which is, well, how do you keep that relationship up to date if it's stored in 2 different places? Who owns the truth for that relationship? I'll get to that. Also for change history, we had to re-implement how we did change history. So we have two different views for a person. There's the person view, and then there's the change history view. And the person view is stored, the journal is the truth, but the person view is stored and the change history view is stored in a single cell. The change history is in a single cell. And that lets us have very quick change history responses. No global scan, no parsing the journal. It's just prepared, ready to go. And it's stored in a ring buffer. So as new changes come in, old changes drop off. So now let's talk about the consistency model. There are three parts to the consistency model. First, we capture commands. Then we record those commands in a journal. And then we compute one or more views for that record. The command is there. Even though Cassandra has atomic batches, we wanted to capture what the user said as closely as possible to what the web request is when they came in, when they said, I want to change the name from John to Johnny or something like that. The journal is the truth, though. The command is not truth. Once it's recorded in the journal, you can reconstruct everything from the journal. And the views are computed from the journal. Let's go into detail on the command. We write once there with quorum, different kinds of quorum for different edits. And there are three different command tables. There's a pending, there's a completed, or an aborted. So if it gets written into pending and the database crashes or whatever and we haven't got into journal yet for that particular command, we have a process that will scan pending and write it into and then pick it up where it got left off. Similar to how atomic batches work, but for our app, at our app level. And the way that a command gets written to the journal is the same. So you could take a command and write it to the journal any number of times, and it would go to exactly the same key and exactly the same row. And so that's how we pick it back up if it gets interrupted. The schema is pretty simple, just a key and a time UUID and a blob binary. We ended up using a binary form of JSON, not message pack. It was, oh, my mind just went blank, I'll remember. So the journal is, you write once there, you don't ever update the journal. If you have any additional updates, you append a new journal entry. And we write journal entries in a batch. So one command could, let's say for that relationship case, person 1, person 2, and R2 in the middle, but R2 is stored under person 1 and person 2, we will write two journal entries. One journal entry to R1 that says the marriage date is 1888 instead of 1887, and over here we'll write the exact same journal entry, just with a different row key, just with a different partition key. So that journal entry is then able to bring both of the persons up to date with the new relationship. So the journal itself is denormalized across persons. Each journal entry is stored as a separate cell, and the partition key is the person ID or the relationship ID. Because it's stored as a separate cell, the journal is size-tiered compacted, and the cells get scattered across SS tables. We rely on compaction at trying to get as much of the journal into one SS table as possible for journal read performance. But journal read is actually not in the critical path. If you're familiar with CRDT words, commutative replicated data type, or distributed, I forgot what the C stood for, but there's commutative replicated data type, and the journal is commutative. That means if you have a cluster partition, and you write one journal entry on one side and another journal entry on the other side, if the partition heals, they come in and they just interleave together, because the primary key is a time UUID, and so they are unique. Partitions converge without conflict because of the time UUID. So an example is, here is a person KWZ3P71, and the command UUID is the last, or the journal entry ID basically, and the content is just a big binary blob. Not big. Journal entries are usually pretty small, be somewhere around 500 bytes to a K or something like that. So now the view. There are multiple views for different uses. This is the key to how we were able to get the consistency model to work. Scanning the journal all the time and rerunning the journal for every single page view would be horrible. Well, so we store views. When the journal entry, when the journal is there and there's no view, then we will compute the view one time and then store it. Every other time that somebody comes back to read, they'll just read the view. The view is stored in a single cell. It's looked up by primary key. There's only ever one column, one cell in that partition, and it's really fast to read. But then you say, well, what happens when a new edit comes in for that person? That edit is incrementally updated into the view. The old view is deleted, and a new view is written. There's a visualization of this. But the view is not canonical data. If, for whatever reason, if there's a partition in the view table, perhaps the view gets written over here and over here on the other side of the partition. They converge. Well, now there are two views. In that case, we rebuild a canonical view from the journal by rolling it up all the way from the bottom. So here's a visualization of that. Here's person 1, and there are two views for person 1. A journal entry gets written to all 3 tables. So when a journal entry comes in, it doesn't just get written to the journal. The journal entry also gets written to all of the view tables. That's so that the view can read, see what's new, and incrementally refresh. When a new reader comes in, he sees the view is there, a new journal entry is there. That reader does the incremental update at read time, writes the result back out, and then returns that result to the user, and deletes the old journal entry and the old view. Now you're left with a new journal and just a single view. In order to do this, we had to make the view table have exactly the same schema as the journal table. ID, command UUID, and blob. So it's a pretty simple schema. All of what we do inside is inside the blob. That allows the journal entries to be written to the view table so that the incremental refresh can happen. That one thing right there about how the views have the same schema is the core of how we're able to get the consistency that we needed. In CRDT terms, the view is a convergent replicated data type. It takes app reconciliation to resolve partitions. Let's see. The steady state, though, is one view of a given type per entity. So let's see. I might have time. In order to get the performance and scale we wanted, we needed to be able to look up by the partition key only with no indexes other than the primary key index, and any cross-entity change had to happen in duplicate on all partition, on all affected entities, basically, is the way we talk about it. And we had to store current state views in order to have fast read. You can imagine that we have more data in Oracle. The data is probably, we did a dump, and it's somewhere around 5 terabytes, I think. When we import it into Cassandra, it's probably going to end up being, we haven't written the migration code for all of the types yet, so right now we're running at around 7 to 8 terabytes, so there is definite data expansion with denormalizing the relationships and writing journal entries to not just persons, but also relationships, and duplicating the journal entries. But it's not that bad. It's not like 10x of what it was in Oracle. And with the strength of Cassandra, just being able to throw disk at the problem is just amazing. The other thing is that we wanted to have some flexibility in the schema. In our Oracle situation, we tweak what's included in the blob. Oh no, we have to do this mass fix-up over 900 million persons on 500 million relationships, and we do those fix-ups like every month. There's a new fix-up that the data quality team has to go run against all of those records. Well, now if we want to change how the view looks, it's easy. We invalidate the views and let the refresh just roll it up from the journal. And we don't just have one view, which is the situation in Oracle. We can have multiple views. So there's the big view with all the person and all the relationships. Well, there's also a different view for traversing the pedigree. This one is much lighter weight, has a subset of the data, and it's totally in duplicate with the other one, but it lets us do the pedigree traversal much, much faster. The flexibility of having multiple views of the same journal data, of the same truth, let us have greater agility in our development process. And so if we want to, the views are disposable. If we want to tweak it over time, we can. So now, what we also had to solve a pretty interesting set of things. We have business rules that disallow certain kinds of edits. Like saying a person is a parent of themselves. We wanted to be able to say, no, that's not a valid edit. Well, it turns out in a distributed database, we didn't want to introduce any kind of locking mechanism to enforce those kinds of business rules. And we also wanted to make it so that two concurrent writers couldn't produce an invalid state. So we ended up with this journal entry writing mechanism that is a read first to double check that the edit is going to be okay, a write, and then a read after. So this is like the bad, anti-pattern, whatever, for a system, but it's what we had to do in order to get the business logic to apply. And we do these reads in quorum, or local quorum, or each quorum for the distributed case. There are only certain kinds of edits that we have to do each quorum. We can survive with local quorum for the most common kinds of edits. So we take the consistency level. We do read of all of the affected entities. We apply our business rules before we do the write. Then we do the write, and then we read again to see if anybody created an invalid state that was a concurrent writer with us. And then if there is an invalid state, we assume we were the problem. And we go back into the journal and we say, that last journal entry I wrote, here's a new journal entry that says journal entry A is no longer valid. That causes a full refresh to happen where A is the journal entry that was bad, B is the journal entry that says A is bad. We strip those out, and then we come up with our prior state. And so the view has the state before that bad write. And we have this concept of appropriate quorum. We support merging persons together. That's a really complicated journal entry that has a lot of different things going on inside that one journal entry. In order to ensure that the resulting state is okay, we're planning on a multi-region deployment, and so we had to do each quorum for that. In order to make sure that it didn't leave it in an inconsistent state. Question?
Earlier about, it kind of falls into this, A marries B, B marries A.
Yes.
Two entries in the journal. What happens if for whatever reason, my application dies after writing the first one, but never writes the second one?
The question is, there's two persons, A and B, and we are writing we're creating a relationship between A and B, saying that A and B are married. What if, when we write the journal entry to A, in between, what if right after we write it to A, our app goes down and we never get the write to be. In that case, when we're writing journal entries in that write in the middle between the reads, we do the write with atomic batches. So logged batches. Cassandra has the feature that I don't remember when it showed up. I think it was in 1.2. But we basically take all of the inserts for A and B, put them in a batch, and hand that off and say, make sure that both of these eventually get written. And it's up to we leave it up to the database to ensure that they're both written. Another question?
So you have these views and you have the journal.
Yep.
I assume there's sort of a software layer that manages the views that need to be updated with the journal, and so that above that you can say, do this at
Yep.
the data layer, not the data layer, but the business logic layer, and then it would also do this read-write, sort of to abstract it out. Is that layer?
So let me try to rephrase or restate. The question is there a piece of software that makes sure that all of the views are up to date after a write? Did I capture that right?
Right, and then also encompasses these special business rules that are
Yep.
software-centric.
Yep, the business rules, that also applies the business rules, that software, yes. That piece of software does exist. It doesn't all happen at write time, though. So when we write to person A, let's say there are 3 different views. We actually use one of those views during this read, write, read, business logic enforcement, but we don't use the other 2 views. The journal entry is still left sitting there in the view, not yet rolled up. It's the first reader that comes in that's responsible for doing the incremental refresh.
And it's not the reader client, it's actually that reader layer that.
Yes, it is we have the logic on the app server is the thing that notices a new journal entry and notices an incremental update has to happen, and who does that and writes the result back out. Did that answer your question?
So like theoretically you have this layer that you could talk to Oracle or Cassandra.
Yep. This is not a like data level replacement, it's an app level replacement. Yes, another question.
Yeah. Irrespective of like if I'm a data consumer, irrespective of whether the data is current in the view or not, I have to always go to the journal, right? Check if there is a record sitting on the journal which is not updated. So I have the redundant read always on the journal. Is it correct?
The question is, do you always have to read the journal to know that the view is correct? The answer is no, you don't have to, because when we wrote the journal entry, we didn't write it only to the journal. We also wrote the journal entry to the view itself. And so it's enough to just read the view table to say, what's my current view? And then if I notice that there are newer journal entries, then I can incorporate those into the view without having to go back and read the journal. Did that answer?
Yes.
Great. Let's see. I think I have 15 more minutes, and I want to save some time for questions at the end. But I wanted to show some of the experience that we had with Cassandra. We built the full prototype on 1.2. We switched over to 2.0 late in the game and didn't have any problems with that. Excellent performance, easy cloud setup. We got some great response from DataStax developers when we had trouble with the DataStax AMI. And we ended up doing our bulk load straight through CQL3. We didn't do anything with computing SS tables on the or in Hadoop beforehand and loading them in that way. CQL3 was fast enough for us. We are going to deploy inside an AWS VPC. The DataStax AMI didn't work for us for that, so it's cost us a little bit more to figure out our own deployment. So the bulk load experience, when we 8.5 billion changelog records in Oracle we wrote a migration piece of logic that turned that into 5.8 billion journal entries. That ended up being 2.5 terabytes LZO zipped. The cluster that we imported it into was High1 4XL on AWS. Each one of those nodes had 2 1 terabyte SSDs. Yeah, it took 11 hours to import a 5-node cluster. It took 5 hours to import a 30-node cluster. We didn't really tune the database very much, but we got 140 writes a second over 128 writer threads. And we ended up getting the best performance by using unlogged batches for our inserts. Instead of inserting each one in a separate insert state, in a separate round trip, we just used an unlogged batch of 20 inserts and said, hey, do this. And we inserted with consistency level 1. Data came in just fine. It took about an hour or two after the import was done for the size-tiered compaction to catch up on the SSDs on the journal. 4 terabytes of disk after importing the journal. Ops Center, community, we had trouble getting the repairs automated. I think that's just a pain spot for everybody. So after the data was imported, we ran something to compute all the views, and we had calibrated our load tests based on the logs that was going on in production. And we were able, this just totally blew our mind. We were able to get 25 times our production load. Right now on the production system right now, we have a little bit of headroom, but you know, let's say if 10,000 more users joined the site and started being active users of it on a weekly basis, we would have some serious issues. I guess I can't really say that it's that bad, but we know we have a limited amount of headroom, and we don't know how much it is exactly. And seeing that we could go 25 times our peak load on commodity hardware out in AWS was just, the proof of concept was a success. Let's just say it that way. People talk about row cache not helping. Well, it certainly helped for us. There's another talk at 2 o'clock, I think, by somebody who's going to present our the tuning on AWS, and he's going to talk about the row cache. We ended up running the active data set with mostly no disk access. We ended up getting bottlenecked on interconnect between the Cassandra nodes. And with the round robin client, we ended up doing token-aware round robin and got 50% more throughput. Ops Center was great for visibility of what was going on, and SSDs made it so that we could do a full repair, a rolling repair, while our load tests were running with at least production, with at least 1x production. So we're definitely going to deploy on SSDs. And this is just a visualization. It's probably hard to see from the back, but there are 4 sets of numbers. The bottom tick is the 50th percentile. The middle one is, let's see, 95th, I think. No, the middle tick is 90th, and the top tick is 95th percentile. And this is from the perspective of a service level request. This is not a web page. This is just for the kind of service level request we need to support the features at the bottom, where we ended up. Log scale graph, our current system is at the top. So the person and relationships for the Ancestor page, 50th percentile was somewhere under a second, and 95th percentile was somewhere under 10 seconds. These 3 graphs are 1x, 10x, and 20x. We saw a little bit of degradation as we went up, but very close clustering, so we were very, very satisfied with the 20x numbers. We're working on the implementation and rollout. We are basically just working on the migration pipeline and reconciling that with the existing truth, figuring out a reconciliation strategy so that we can have incremental update. We're going to make a flip. We're going to flip the switch, not trying to do everything bulk loaded, but we're going to practice incremental as we go, and then there will be an outage, a write outage while we flip the switch. The consistency model that I talked about is separate code. I haven't got permission to open source it yet, but if there are people who are interested, please come up and talk to me after, and I'd be happy to try to run that up the pole. Right now, FamilySearch isn't an open source first kind of place. I wish it were, but I would be more than happy to make the attempt if you're interested in the code. And so, let's see, I think I have 2 or 3 minutes for questions. Any other questions?
With the number of journal entries that you have,
Yes.
with the number of journal entries that you have per entity in the system, do you worry about rows getting too wide?
Yes.
Partitions getting too wide, and what do you plan to do about that?
The widest row is about 10,000 cells. We haven't seen a situation where the number of journal entries would go into the 100,000s in the foreseeable future, but if it gets to 20 or 30,000, we're going to chop it off, summarize the old history, and throw it away or archive it. Yep.
Hi. See what I think a cool feature would be on the platform is when people enter data,
Yeah.
have a timeline of who's edited data on somebody's record over time.
Yeah.
Because you guys are archiving data about people's life.
Yeah.
But what's interesting as well is to archive who thinks what at some snapshot in time.
Yes.
I think that would be cool.
Yeah. Yeah. A timeline of edits. Yeah. We're exposing timeline for the person, but timeline for edits is also a great thing. Thank you for coming.